So for the second approach in solving problems with artificial starting solutions, we will discuss the two-phase method. So in the Big M technique, the use of the penalty M, which by definition must be large relative to the actual objective coefficients of the model, can result in round-off errors that may impair the accuracy of the calculations. So the two-phase method alleviates this difficulty by eliminating the constant M altogether. So their process is basically the same, but the difference is that the two-phase method doesn't use the constant M in the solution. So this is the summary of the two-phase method. So for phase 1, we put the problem in equation form and add the necessary artificial variables, exactly as what we did in the Big M technique. So this is to secure a starting basic solution. Next, we find a basic solution of the resulting equations that, regardless of whether the LP is a maximization or minimization problem, always minimizes the sum of the artificial variables. So that is for the objective function. If the minimum value of the sum is positive, so meaning if the values of R1 and R2 are positive, or if we cannot dispose the artificial variables, if we cannot have them as the living variables, the LP has no feasible solution, which ends the process. So recall that a positive artificial variable signifies that an original constraint is not satisfied. So otherwise, if the artificial variables are disposed or their values are 0, we can now proceed to phase 2. So phase 2, we use the feasible solution from phase 1 as a starting basic feasible solution for the original problem. So we are still dealing with the problem from the orange. So this is problem, the primal form. Mean z is equal to x1 plus 3x2 subject to 3 constraints. 1/2 x1 plus 1/4 x2 is less than or equal to 4. x1 plus 3x2 is greater than or equal to 20, and x1 plus x2 is equal to 10. Then all those variables should be greater than or equal to 0. So we will transform them into their standard form, same as what we did in the Big M technique. So that is for the constraints. In constraints, if the inequality sign is less than or equal to, you will add positive s to transform it into its standard form. If the inequality sign is greater than or equal to, you will add negative s plus r. And if it is an equal sign, you will just add positive r. Then it was indicated in the summary that regardless of whether the LP is maximization or minimization, the objective function will always minimize the sum of the artificial variables. And since we have two artificial variables here, we have R1 and R2, our objective function, starting objective function, will become mean R is equal to R1 plus R2. So we will use R instead of C in the phase 1. So this is for the phase 1 only. And then, yung right-hand side is the summation of the artificial variables. So since we only have two artificial variables, we have two of them on the right-hand side. But if you have R3, R4, R5, or you have a single artificial variable, that should be proportional to the number of variables in your constraints. So we have to transfer the terms on the left-hand side. So that becomes R minus R1 minus R2 is equal to 0. So after successfully transforming all those equations into their standard form, we will proceed with phase 1. So at phase 1, Same as in the big M and in the simplex method, just have to formulate an initial tableau. So that contains the basic, yung Z now becomes R, then S1 for the first constraint, R1 for the second constraint, and R2 for the third constraint. So this is just the same as in the big M technique. The only difference is yung 0, it is now an R row. So the column headings are X1, X2, S1, S2, R1, and R2, and the RHS. So you just plot all those values. So for the R row, that is just R1 has a coefficient of -1 and also R2, and then RHS is 0. And then the rest is the same as what we did in the big M technique. So for the S1, got those values for R1 and for R2. So this is just the same. The only difference is the R row. And then after creating an initial tableau, same as in the big M technique, you need to have a new initial tableau. So a new initial tableau must be constructed first before proceeding with the usual iterations using the Gauss-Jordan computations. So you need to have, or you need to follow this equation. So to create a new R row coefficient, you need the old R row coefficient plus the summation of the R and row coefficients times 1. So in the big M technique, you multiply the coefficients by M. In the two-phase method, you multiply them by 1. So this is the initial tableau, and this is the equation that we need. So same, you just have to copy all the columns and rows except for the values in the R row, because we will use this equation to find the new R row coefficients. So for example, the value that will be placed under X1 is the old R row coefficient, so that is 0, plus the R and row coefficient. So we have two values. So we'll just have to add up the resulting values from those two artificial variables multiplied by 1. So their row coefficients are both 1. So the equation is 0 plus 1 times 1 plus 1 times 1. So the resulting value is 2. Then for X2, the old R row coefficient is 0. So here is 0 plus the R and row coefficient for R1 is 3 times 1 plus 1 times 1. So the resulting value is 4. For S1, the old R row coefficient is, so here is 0 plus 0 times 1 plus 0 times 1. That is 0. For S2, that is 0 plus -1 times 1. So here is -1 times 1 plus 0 times 1. So the resulting value is -1. For R1, we have -1 plus 1 times 1 plus 0 times 1. So that is 0. For R2, we have -1 plus 0 times 1 plus 1 times 1 is 0. And for RHS, we have 0 plus 20 times 1 plus 10 times 1. So that is equal to 30. So that is our new initial tableau. So since in phase 1, our objective function is minimization, since it is required that it always minimizes the sum of the artificial constraints, we just have to look for the most positive value in the 0 to identify the entering variable. Then the living variable is the same with all the methods that we have discussed. It is the least positive ratio. So looking at our new initial tableau, our most positive value in the 0 is 4. Then find, or x2 now becomes our entering variable. Then find the least positive ratio by dividing the RHS values by the corresponding values in the pivot column. So for the R, we don't usually use it as a living variable. For S1, so that becomes 4 over 1/4, so that is 16. For R1, that is 20 over 3, or 6.67. And then R2 is 10 over 1, or equal to 10. The least positive ratio is 6.67, so our R1 is our living variable. And after, proceed with the Gauss-Jordan computations and solve for the values in the iteration 1. So this is the resulting iteration 1. So I will not solve them one by one, just have to identify or verify if the values here are correct. So after that, you need to find again if there is a positive value in the 0. So we have 2/3 and 1/3, and the higher value from those values is 2/3, which is under x1. So that is now our entering variable. And then find the least positive ratio. So S1, we have 7 over 3 divided by 5 over 12. So that is 5.6. For X2, we have 20 over 3 divided by 1/3. So that is 20. And then for R2, we have 10 over 3 over 2/3 is equal to 5. So the least positive ratio is 5, and then R2 is our living variable. And after solve using Gauss-Jordan computations, this is the resulting table. Then we can see from the R row that there are no positive values. So sorry, this is R in the R row. So we don't have any positive values here. And then the sum of the artificial variables is also not positive. We were able to dispose the artificial variables under the basic column. So if the sum of the artificial variables is not positive, that is the end of phase 1. So after successfully completing phase 1, you need to proceed to the phase 2 to obtain or to find the optimal solution. So to proceed with phase 2, you will only eliminate the columns of the artificial variables in the last iteration and then use the original objective function. So this is our last iteration. Just need to eliminate the columns of the artificial variables and then use original objective function. So here is our original objective function. Mean z is equal to 2x1 plus 3x2. Then you need to transpose the terms to the left-hand side. So that becomes c minus 2x1 minus 3x2 is equal to 0. And then just need to plot those values in the initial tableau. So if you can see, the values in the S1, X2, and X1 rows are the same, or they were just extracted from the last iteration in phase 1. And then yung 0, you just need to plot the values from the original objective function. So here is -2, -3, 0, 0, and 0. So the rest of the values here are extracted from the last tableau in phase 1. So after that, after creating an initial tableau from phase 2, you need to create a new initial tableau. So ito yung new thing about the artificial starting solutions. After the initial tableau, you need to create a new initial tableau in the big M or in the 2 phase. So in the new initial tableau for phase 2, so the new 0 coefficient is equal to the old 0 coefficient plus 2 times x1 numerical coefficient plus 3 times x2 numerical coefficient. So yung 2 from the equation is from the original equation, the coefficient of x1 in the original objective function. And then the 3 here is the coefficient of x2 in the original objective function. So this is not permanent. This is dependent on your original objective function. So for example, if the original objective function is 5x1 minus 7x2, for example. So your coefficient here will be 5, and then here it will become negative 7. So it is dependent on the original objective function. So we need the initial tableau. So the new initial tableau, just use the formula. So just copy all the rows except the values for the 0. So for example, the value that we will place under x1 will be negative 2, that is the old 0 coefficient, plus 2 times 1, which is the x1 numerical coefficient, plus 3 times 0, which is the x2 numerical coefficient. So the resulting value is 0. Then for x2, that is negative 3 plus 2 times 0 plus 3 times 1. You just have to follow this equation. So the resulting value is 0. For s1, that is 0 plus 2 times 0 plus 3 times 0. So that is 0. For s2, that is 0 plus 2 times 1 half plus 3 times negative 1 half. So that is negative 1 half. Then for the RHS, so that is 0 plus 2 times 5 plus 3 times 5, or 25. Then from the new initial tableau, we can see there that there is no positive values in the 0. So we cannot have an entering variable. So phase 2 ends. And if you're able to come up with a tableau like this, where you cannot identify a positive value in the 0 that can be your entering variable, you have obtained an optimal solution. So just the same as in the Big M technique, the values, so we're solving a single problem, so basically their value should be the same. So x1 is 5, x2 is 5, s1 is 1/4, s2 is 0, and then the values of the artificial variables are 0. Remember that if their values are positive, your equation or your problem does not have an optimal solution. So the problem has an infeasible solution. And then your z is 25. So the answer is the same as in the Big M technique. Then you can do the checking. So it's just the same. You need to substitute all the values and see if their equations are, or the resulting values are the same. So that is the two-phase method.